So this is On Defining Proofs of Knowledge by Bellare and Goldreich. This is like one of the earlier fundamental papers on proofs of knowledge, and it corrects some of the previous papers' kind of misunderstanding or like informality, lack of formality, I think is probably the best way to put it. So that's why this is an important paper. This is a very difficult paper because what you realize about 5 pages into it is that they're writing math as English. So if you start reading it as English and you think they're writing in English, it's just nonsense. It's just word salad. But once you realize that they're writing math equations as English, then it starts to make sense. So I'll try to go through some of it. Like I said, I've only prepared the first 5 pages, and then maybe next time we can kind of continue on into the formalism. But this will be like a good introduction into the topic. So the notion of a proof of knowledge is used in the construction of cryptographic protocols. Commonly, the lacking formalization, that's basically what I was just saying, or it's unsatisfactory formalization. And so this paper sets to basically reverse that or improve that. And I'll just kind of proceed, if you have questions or things that you want to talk about, just feel free to bring them up. So the fundamental work gives intuition and clues, they're saying, about the notion of a proof of knowledge, but it does not provide a formal definition, which is a problem. Then there's been subsequent works that had formal definitions, which they say are commonly cited by these guys, Fage, Fiat, Shamir. But they're saying it's not satisfactory, and that's what they're going to talk about. So first, they want to describe these flaws, and then second, they want to fix them. Okay, so, and then a lot of this is going to talk about, and this, I'll try to go slow. It's hard to understand. It's hard for me to understand. But let's try to reason through it. And I found I was not understanding it really until I tried to come up with some examples. So maybe the funnest or the best thing that we could do would be kind of come up with examples that describe this. So both have the common attempt to capture provers who convince with probabilities that are not non-negligible, meaning that they have a probability, correctly addressing what we believe is one of the main flaws of the definition. So that's the conceptual problem that we're going to be talking about. So, and they'll reuse this super polynomial time. So they're going to be talking about a lot about, the ability of machines to actually compute a solution to a problem. So one of the things they're saying, and so that's also referred to as NP, which is just a computer buzzword, which means non-polynomial time. So typical computer algorithms might be, linear or quadratic or, whatever, go by the, cube or something like that. That's polynomial time. But then there's other algorithms that, essentially exhaustive searching or things that exhaust the whole space, which are considered non-polynomial time. And so, people think of the entire totality of everything that computers can do as being both of those sets, not, non-polynomial and polynomial time operations. So that's what they're going to discuss, and that is basically the idea is that they're going to bring computers in to the discussion and say that computers can actually do this work. It doesn't have to be just between two parties, two human parties. So here's their basic definition, which they're going to use throughout the paper. A two-party protocol consists of systems of proofs of knowledge if whenever one party is convinced, then the other party knows something. Okay, so it's pretty general. And I think they're having a problem with the English language because they they're using all these quotes and they're just really trying to make a very specialized argument just by their notation, which is another thing that's confusing about this paper. But I think what they're trying to say is that these are just like abstract English terms, and they require mathematical definition to be a little bit more useful. So let us consider the special case of an object of knowledge that is a witness to membership of a common input. So basically, like, a record in a database. Something exists, and this is really important that there's this predetermined language that is computable. And so, what does this mean? Like, this is kind of like buzz speak or buzzword, but what this means is like that they have a shared agreement on an algorithm or an approach. And like what I think of is like Reed Solomon codes. You could think about, I could send you a system of linear equations, and if you can solve it, you know that the data is valid. Or you could also think about like public key cryptography, where I can send you my public key, and then I can sign a message with my secret key, and then you can use my public key using this, NP strategy of public key cryptography and determine that I had indeed signed it. So we have to agree on both sides on what they're calling a language in NP, which is just going to be that algorithm. It's the agreed upon approach. So consider the object of knowledge that's satisfying some conjunctive normal form formula that's given as input by both parties. So this just means it's some mathematical formula. Hence, and it doesn't have any strange properties. It's something that we can understand and a machine could easily process. So the two-party protocol constitutes of a system of proofs of knowledge by satisfying assignments if whenever the verifier is convinced, then the prover knows. And so that's the restatement of the first sentence. Okay, I'm not going to talk about their quotations. I think that's like too much on the quotations. We know what convinced means. Um, so following, let's see, I'm skipping. So there's a question of like what it means to know something, and I think this is an interesting question, right? Like, so a student takes a test, they prove they know something by answering questions about it, right? And so that's kind of, I think, what this is getting at. If the prover knows something, then they can satisfy the algorithm or the approach. Um, and they're also saying, okay, well, this is not going to be very useful if we don't have an efficient way of doing this, right? So, like, if your solution requires some exhaustive searching or something like that, but it doesn't make it feasible to compute in a reasonable amount of time, then it's not going to be a good algorithm. So we're going to require that there exists an efficient algorithm called the knowledge extractor that is on the input for the formula of phi. And so phi is just that thing that we were talking about earlier. It's the language, the NP language. That's just the function that's going to be computed in the NP language. So if it was public key cryptography, it might be solving, an exponential formula or an elliptic curve formula. So given the oracle and the prover both have access to it. So then it's able to output the result of that member of the language. So that's what they're saying here. So basically, I was thinking about one example where imagine, I wanted to prove to you that I know how to compute the algorithm, or I know how to compute pi, right? And so pi is like a Taylor series expansion. It's 4 times the arctangent of 1, so I can use calculus to take the derivative of the arctangent and expand it out as a series, and I could send you, a sub naught, the first digit of the series, and I could send you a sub 1, and I could send you enough elements of the series until you could add up, 1,000 digits of pi, and then you would be able to believe that I knew an algorithm for getting pi, and I didn't even have to tell you exactly what my Taylor expansion was. So it's something like that, and that's what, so each of these phi's would basically be the element of the series. So that's sort of like the general case. So the problem is to deal with um, a time when the prover may convince the verifier with some probability less than one. So this is, obviously it's kind of just simple and intuitive. If I can convince you with probability one, like I send you the hash code, the cryptographic hash code of my document, and you look up that document in a document database, then you have probability one. It's super simple, but that's not too great, right? Because I've essentially revealed to you the exact document. I haven't hidden the knowledge, which is kind of the goal. And then there's also problems around this. Like if I'm convincing you with probability less than one, I'm kind of saying, well, what probability is that and how much are you willing to accept? Are you going for a 99% probability? So on and so forth. So that's what this is saying. So, this is sort of like the student taking the test, right? So the student, they can tell you about the Three-Fifths Compromise and they can tell you about the Kansas-Nebraska Act. So you're starting to get some understanding that they understand about the Civil War. But, are you 25% satisfied that they kind of understand about it? And you kind of keep asking them questions until they can succeed in outputting the satisfying assignments and expected polynomial time, right? So, maybe there's 100 questions on the test, and that shows the student has learned about the American Civil War. If they get a significant portion of those right, that's pretty much what this is saying. So we're trying to drive that probability to one as best we can, is what they're saying. Um, so this is where it kind of like gets a little bit bonkers, and I'm just going to do my best. So this interpretation is valid also for epsilon if epsilon is any non-negligible function of the length of the input of phi. So what we want to say is, so we're trying to prove this with some bound, some lower bound. So it says it's bounded by below. So, and they're using this polynomial n to the minus c, which if you remember, I don't know, can you see my Wolfram? Yeah, yeah. So it's basically bounded below. Like as you increase it, it goes down, but it's giving you some lower bound. It'll never be less than this. So, you could agree that, oh, okay, well, we have a good solution as long as all of my answers are sort of above this bound. That's what they're saying. But what should be required otherwise, right? So that's kind of like the easy case where I can say, oh, I'm just going to give you the probability I want. And if all of your answers fall within that probability, then, everything's great. But are there other problems? There are other, things that can happen. So that's what we're going to talk about. So most previous formulations, that's what they are criticizing in this paper, don't have any specific requirements. So this is a problem, and that's what we're going to talk about. And so it's going to talk about when proofs of knowledge appear as subprotocols inside larger protocols. So one of the challenges might be, if I'm trying to agree with you on the cryptographic algorithm that we're going to use, and I don't want to reveal to you which cryptographic algorithms I know about, then we need to have a little bit better than just like kind of like a hopeful understanding, right? Like if we're saying, we're just kind of like getting it to this point where we both agree that it's good enough, these inadequacies might come to play and actually be dangerous when these are part of some sub protocol within a larger protocol where you're expecting it to be rigorous and secure. So they're saying basically, if you have these inadequacies, you can't really depend on this to work in some sort of cryptographic protocol, right? Because how can you depend on the construction of a cryptographic protocol when you don't trust one key element of it? Okay. So this is just really dense, and this is what I was referring to as mathematical language written as English. So this is just them putting it into words. and I'm skipping sort of the middle. So a key observation which has been overlooked by this argument is that a sequence of probabilities can be neither negligible, smaller than the polynomial that we have suggested, right, because that was the proof that it works, or non-negligible for all of the cases, for all of the elements. So let's talk through that a little bit, or let's keep going a little bit, and maybe we can kind of understand that better. It's, for me, it's hard to understand just intuitively what they're trying to say. So what we can imagine, so one consideration is you could imagine when elements of the language that we're describing have some negligible probability of being a member. So what I was trying to think about was like a music service like Shazam, where, it takes little pieces of popular music, it slices it up maybe into like 1 second long, creates a hash code of that, puts the hash code in the database, and then if it can get enough sequences of some popular song, it can convince itself that it knows the song, right? And so, like, you could imagine a negligible scenario where, like, say, instead of like a 1 second sequence of the song, you just took a single note. And so, in my mind, I'm thinking about like, well, there's 12 notes, right, in music. They're not all equally common, but most of them will be presented in, many songs, popular songs. So if you're just giving an infinite sequence of notes, you're actually not finding, so sorry about that. Where was I? So that, like, if they're giving you information that essentially it's just uh, like negligible probability of revealing the information, it's not very useful. And then you also can think of other kinds of events. So that's what this is going to talk about down here. So what happens if the prover does not convince the verifier with a non-negligible probability? So we consider the possibilities. There are an infinite sequence of formula, right? So this is what we're talking about this language. So again, this is like what we've agreed upon. These are the polynomials that we can solve using our two different machines to agree upon the knowledge. So that the prover convinces the verifier on a common input is some probability that we're requiring. And so K is like, the number of entries that we're going to send. So like I was saying, like, we're going to try to send, 10 samples, right? That's the number of elements that I'm sending, I believe. Let's see where. N is the length of the polynomial. N is the length of the function. And K is the number of literals of the longest clause. I think that's right. I'm not sure. So an important observation of the sequence of probabilities defined by the above prover and formula is neither negligible, so smaller than that for all C and all sufficiently large n's, nor non-negligible, so bigger than that. So in this case, they're saying that there's kind of like two cases. So one is the case where you like send one single note and it correlates to all songs. Then another kind of case might be where I send you, so let's say I have a popular song and, I pull a phrase from it and I send it, and that correlates to songs in your database, but it's not necessarily the same song as I sent, right? So I could send you 10 phrases from music that are so common that they exist in many, many songs. And so essentially I'm able to prove to you that I have a popular song, even though what I'm sending to you, I just know are like really common phrases. So I'm basically doing like a ciphertext attack to be able to prove to you that like I know your data set well enough that you're going to believe me. So I think these are the two cases that they're kind of talking about. And then again, they're talking about that subprotocol. So I think they're trying to make the argument that, if it has these weaknesses, then you can't use it as a subprotocol inside of your application. Um, so using a reasonable definition of proof of knowledge, one should be able to prove the statement that we have not communicated any knowledge. And so then they bring up this concept of zero knowledge. And so zero knowledge is essentially, so if we take it back one step further, like thinking again about the Shazam analogy, if I'm revealing to you, you're kind of like given this knob that you can turn of the probability that you want to agree that I have the knowledge. So you can require me to keep sending you samples. But if I keep sending you samples of my song, I'm also revealing information to you. So in a way, it's kind of that algorithm would be problematic, the one that I'm suggesting, because I'm actually sharing with you knowledge about my song. And if I give you 10 samples, just like the Shazam service does, it would be able to reconstruct the song uniquely. And you could essentially de-anonymize the information. So, in other words, the zero knowledge property cannot be demonstrated using previous formulations because they have this weakness. So, a more concrete and practical setting can help further our point. So, consider a subprotocol, and this is one I referred to earlier, inside a multi-round encryption scheme. So we're going to use a chosen ciphertext attack. So the idea is that I want to prove to you that I know how to encrypt something so that I can take, the Declaration of Independence. I can encrypt it using DES. I can send it to you, my cipher that I resulted in. I haven't revealed what I put in there to anyone in the world because it's encrypted. And then you can take the same thing. You can encrypt it using DES, and you can see that the ciphertext that I got equals your ciphertext, and that way you can agree with me that I know the algorithm for DES. So, and in that case, you might successfully return, so the decryption module returns the decryption of the chosen ciphertext, so you would return to me the Declaration of Independence only if it was convinced that I knew DES. So the party is asking already knows DES, right? So you're not giving them any information. So this is a special case of the application that they were talking about. So when they refer to these subprotocols. So using previous formulations of proof of knowledge, it cannot be proved that the above decryption module is zero knowledge. So I think what they're saying here, so under a chosen ciphertext attack. So what they're saying here is like we have all these encryption algorithms that we use, basically the security of them, using a particular multi-round encryption scheme, we believe it to be secure, but it can't necessarily be provably made to be secure. We just, the NSA hasn't cracked it yet, so we just trust them to be secure. So they're kind of using this thing, well, we can't necessarily use that encryption scheme as a proof because there is no proof that there's not a chosen ciphertext attack. So the idea would be, if the attacker on my system, like I use the Declaration of Independence, the Declaration of Independence, if the man page for fork on Linux also encrypts to the exact same ciphertext, that's the chosen ciphertext. So I could say, I want to know what document they're sharing. And so I could convince them by encrypting the man page for fork on Linux and sending that to them. And then they compare their ciphertext, they find it to be the same, and then they reveal to me the Declaration of Independence, right? That's the chosen ciphertext attack. And usually the advantage is in the attacker, because if you have an open beacon on the internet, the attacker is often free. You could think about like password hacking, right, where people just try over and over again, trial and error. We think one of these is going to work. They could just keep trying chosen ciphertexts until it finally succeeds, and then they get what they want, which is the information. So that's what they're talking about here. And the idea is that the security has not been proven, right? Because these algorithms, these cryptographic algorithms that we depend on, their security has not been proven. But it's rather hand waved. So it's kind of like and I'm hand waving right now. So you can't have like this inadequate formalization with all these weaknesses that depend on potentially like these probabilistic determining values that could be in fact not what we believe them to be, because the whole protocol will fall apart. And it says it's a typical example actually of how you would want to do proofs of knowledge, how you would want to use proofs of knowledge, which seems reasonable. I could think about like negotiating a protocol between two servers, right? You would want to be able to reveal the most secure algorithm that's known by the other server without revealing all the algorithms that you're aware of, because maybe that other server is not trusted, and you don't want it to know what cryptographic algorithms you're aware of. So it kind of makes sense. Okay. So all that is, so previous formulations of proof of knowledge are only meaningful in the case that the prover can convince the verifier with non-negligible probability. So you should not make the mistake of saying that events which happen with a probability that is not non-negligible can be ignored. Like we can't ignore the fact that, I'm going to send you all those phrases from popular music and you're just going to believe me that I have a popular song, even though, I haven't actually convinced you because I don't have one. So you can't just ignore them because they're non-negligible. And this is an interesting point, that negligible is not the negation of non-negligible. I think they're just making the point that those two cases are not the opposites, like what we described. Those are just two different sets, two different types of problems which happen to the algorithm. They're not necessarily the opposites of each other. Okay. So this is kind of like, this is more, so this is just like, telling us about what they are trying to do. So the requirement that the knowledge extractor always succeeds in the average number of steps it performs is inversely proportional to the probability that the prover convinces the verifier. So basically, they're trying to guarantee convergence. And all previous definitions refer only to provers which can be implemented by probabilistic polytime programs. So they're actually expanding this to be NP, so like everything that a computer could compute, but they do say that it has to be efficient. In some works, it is even claimed that it makes no sense to talk about the knowledge of computationally unrestricted machines. That's an interesting statement. I don't know if they're thinking about like quantum cryptography or something like that. We strongly disagree with such claims and point out that previous definitions have considered only restricted provers because of technical reasons, right? So they can't make their proofs because they're subject to some mathematical limitation. But we really do want to incorporate that in our reasoning. So we want to arrive at this uniform definition of proofs of knowledge, and we want it to be formal. All right. Okay, so most proofs of knowledge are constructed by iterating some protocol. That's what we talked about. Like say, imagine like the case of pi, where every element of the sequence is the atomic protocol, right? Each it can be written as a single simple equation, or like public key cryptography, where each it's some simple equation that you're solving, this exponential function or an elliptic curve function. So typically these atomic protocols have the property that you can easily lead the verifier to accept the probability even when they have no knowledge whatsoever, right? So it's just you look at it, that's a function that's it's a truthful statement, right? Once you've solved the function, that's kind of I think what they're saying. So these atomic protocols do prove some knowledge of the prover in case it is able to convince. So you have to understand what the function itself is stating, right, and what you're putting into it. So that's one of the challenges. And that's what we were talking about earlier, that like I was revealing the song if I have it by looking in the database. So previous definitions of proof of knowledge were unable to capture this phenomenon. They were only able to say that what it means for sufficiently many iterations of these protocols to be proofs of knowledge. So in other words, they said that, if you just keep going, eventually you're going to believe it because there's some non-negligible probability. So but then that's going to become a challenge to protocol design, because you don't want to just keep iterating forever to agree on what protocols you're using. There has to be some built-in efficiency. So they want to know how much error in the knowledge that there is for the given proof. And so that's going to be done later. And they talk about a special case, the error is 0. This is important for some applications. So that would be like the example I said about, I send you a hash code of the Constitution, right? So there's no error. Like one party already knows the information, so he's going to send it back if he agrees that you know it. Okay. All right, and so then this is where we kind of head into the formalism. So that's where I stopped. It's pretty deep and involved. Any thoughts, questions, things you think I said wrong, or?
No. I really like the example of Shazam, and I think that when talking about probability and thinking about probability in general, just working on theory is very difficult.
Yeah.
I mean, I remember even from school that it's not intuition doesn't really work immediately when reading this stuff. But this example of Shazam, I think it's actually really good. And when I'm thinking about it now, it's a great model to think about it, because you can experience these two problems you were talking about. So the one that I am sending you, just a few, 100 milliseconds of the song, and many can be true. And the same with too many examples, so you can basically recreate entire song. So when thinking about example like that, it's pretty easy to understand. But coming with this example is difficult. So translating this document, this paper to these examples, I think this is the most challenging part.
Right.
But yeah, nice to I am sure that when me reading the document, I wouldn't came with this Shazam example. So it helped a lot, and I think what I'm now start thinking how they want to implement it in this DAOs for voting. So
right.
Trying to translate it, and I think that after this presentation, at least for me, it will be easier probably to watch some YouTube videos when someone explains the stuff like you just did, rather than just reading this paper. So
right.
Yeah.
Yeah, it's the same problem for me. It's exactly thinking, I totally parallel your thoughts. And, when I read this, it just had no ability to understand it. And, I didn't start to understand it until I started to think of the example, actually. Because it is just like this kind of like abstract math. And, yeah, I agree with you that kind of like finding the right resources, can be critical to understanding how these things work.
And I think it's true, especially when you are starting dealing with this topic in general. After when you read a few papers and I don't know, watch few videos and have these examples in your mind, I think it's then easier to go deeper and understand more. But for me, where my knowledge was pretty close to zero in this topic,
zero knowledge.
It's great with this example. So yeah, I appreciate your time explaining it, and I think I will try to watch some videos to hopefully to learn more about it